Usually, when you build a house, the blueprint is the thing you use right at the beginning.
Right.
It is the plan.
Yeah, exactly.
And once the drywall is up and the paint is dry, you basically roll that blueprint up, shove it in a tube somewhere, and, well, you forget about it. The physical building is the reality now, and the blueprint is just history.
But imagine if that blueprint was permanently physically linked to the house itself. Like if you erase a wall on the paper, the actual wall in your living room just vanishes.
Oh, wow. That sounds terrifying.
Right. Or if you stole coffee on the way out, half of your actual roof just collapses.
Yeah.
That permanent, really high stakes link is exactly what we are exploring today. We are looking at mastering Terraform state, specifically tailored for anyone who is preparing for the HashiCorp Terraform Associate 003 exam.
Yeah, and our mission for this deep dive is to completely demystify this concept, using the official documentation and the exam objectives. We are going to break down why state is the ultimate source of truth, how to protect it, and, well, how to operate on it safely.
Because if Terraform state is this magical blueprint of a building that is already built, you have to understand what actually happens to your cloud infrastructure when you accidentally mangle or erase that blueprint.
Because disaster definitely happens.
It does. State is Terraform's actual memory of what exists in the real world. Without it, Terraform is entirely blind.
So it's not just a read-only log.
No, not at all.
Yeah.
When you declare a server in your code and run an apply, Terraform doesn't just build it and walk away. It records the specific ID, the metadata, and the exact configuration of that server into a local file.
And if you lose that file...
If you lose it, the next time you run Terraform, it looks at your vast cloud environment and simply says, I have no idea what any of this is. I didn't build this. It basically have total amnesia.
Right. It is the brain, the memory bank. And for you listening, especially those just starting out writing your first modules on a laptop, that memory lives in a local file called terraform.tfstate.
Yeah, it sits right there on the hard drive.
Exactly. Right in the same directory as the code. Which seems simple enough. But, okay, let's unpack this a bit. If Terraform's whole job is to manage the cloud like AWS or Azure or Google Cloud, why does it need a local memory file at all?
That is the big question.
Right. Like, why can't it just query the cloud provider's API directly, look at what was already deployed, and figure out the current state on the fly?
So relying solely on the cloud provider's API fails on three critical fronts. And those are performance, metadata mapping, and ownership boundaries.
Okay, let's start with performance.
Right. Consider an enterprise cloud environment with like 10,000 distinct resources.
Yeah.
Security groups, subnets, instances, load balancers.
That's a lot of stuff to keep track of.
Exactly. If Terraform had to query the AWS API for the real-time status of every single one of those resources every time you ran a command, the HTTP overhead alone would be massive.
You would just hit API rate limits almost instantly.
Instantly. A simple infrastructure check could take hours just waiting for the cloud provider to respond.
So the cloud provider would essentially start throttling you because you were running a massive audit every single time you want to change, say, one tiny tag on an EC2 instance.
Precisely. So the state file acts as a high-speed local cache. Terraform only checks the cloud to verify the specific things it already remembers.
Okay, that makes total sense. What was the second front? Metadata.
Yeah, metadata mapping. Terraform tracks dependencies and relationships that the cloud provider might not explicitly care about or, even expose.
What do you mean by that?
Well, it builds an internal graph, like a topological map of what must be created or destroyed first. For instance, it remembers that a specific database was created before the application server that connects to it.
Oh, giving it the crucial context of how to tear them down in reverse order safely.
Exactly. The Cloud API just sees a database and a server. It doesn't necessarily know the historical sequencing of how your specific deployment needs them managed.
Right. It doesn't know the story of your infrastructure.
Yeah.
And the third front was ownership, which I think is fascinating.
It is arguably the most important one. Terraform operates in a shared reality. It needs a rigid boundary to know what it manages versus what a separate team or some, rogue script manually created in the AWS console.
So it's drawing a line in the sand.
Yes.
Yes.
By consulting its state file, Terraform essentially says, I have records for these 50 specific resources. I am responsible for them. I will entirely ignore the other 5,000 resources running in this account.
That ownership boundary makes total sense. But relying on a local TF state file introduces a massive vulnerability the moment you are no longer flying solo.
Oh, absolutely.
Like if that file is sitting on one engineer's laptop and they decide to go on vacation, the rest of the team is completely locked out.
They don't have the memory file.
Right, so they can't safely manage the infrastructure, which means the team has to share the state file somehow.
And that shared access introduces the classic disaster scenario.
Okay, let's visualize this for everyone listening. Let's say you have a development team scaling up. They decide to move their infrastructure to AWS, and they are sharing the Terraform code repository.
Sounds like a standard Tuesday.
Right. And they somehow have access to the same centralized tfstate file, maybe on a shared drive, but without any specific safety mechanisms in place. So my teammate and I are working on different tasks. We both type Terraform apply and hit enter at the exact same millisecond.
You've just created a race condition.
And that leads directly to state corruption, right?
Okay.
Because what actually breaks inside that file? Are we just splitting the blueprint in half?
Basically, yes. Terraform is fundamentally a process of reading the current memory, calculating the required changes, and then writing a completely new updated JSON string back to the file to save its new memory.
So if two separate processes are trying to write their own version of reality to the same text file at the exact same time.
The underlying JSON structure just breaks. Yeah, process A opens the file to write its string. Process B opens the file a microsecond later to write its string. They literally overwrite each other's data blocks midstream.
So you end up with a file where the top half reflects process A's infrastructure, the bottom half reflects process B's.
And right in the middle, a JSON bracket is sliced in half. The syntax is entirely invalid. The next time anyone runs Terraform, the parser crashes, the file is unreadable, and the memory is functionally destroyed.
Because there is no traffic cop. There is nothing standing in front of that file managing the queue.
Exactly. That race condition is exactly why HashiCorp realized state couldn't just live on a laptop or even just be tossed into a shared network drive without a control mechanism.
Which brings us to the industry standard cure, remote backends.
Yes. Centralizing the state file in a secure remote location designed for collaborative environments.
And for teams working in AWS, the gold standard pattern, the one heavily featured on the 003 exam, is using Amazon S3 in combination with DynamoDB.
It is a very deliberate division of labor.
Right, so let's use an analogy here. We use S3 as the highly durable, centralized vault. S3 simply stores the tfstate file so everyone on the team can reach it.
Right, it's the giant steel safe where we keep the blueprint.
But S3 itself doesn't actually care how many hands are reaching into the vault simultaneously. It just holds the object.
And that is where DynamoDB steps in. DynamoDB is strictly used for state locking. It acts as the bouncer standing in front of the S3 vault.
So when you run Terraform apply, your local Terraform binary reaches out to DynamoDB first and requests a lock.
Correct. DynamoDB writes a specific item to a table, essentially a cryptographic lease, saying this specific user currently holds the lock.
So once you have the bouncer's approval, only then do you reach into S3, pull down the file, do your calculations, push the updated file back to S3, and finally tell DynamoDB to release the lock.
Exactly. And if another engineer tries to run an apply while you hold that lock, their Terraform process checks DynamoDB, sees the active lease, and immediately aborts.
Which is great. It just stops.
Yeah, it prints a clean, safe message to their terminal saying, error acquiring the state lock.
Which is infinitely better than destroying the memory of your entire production environment.
So much better.
Now, if you are taking the 003 exam, this specific relationship is one of the most common traps you will face.
Oh, 100%. The question will usually frame a scenario just like the development team we discussed. You know, a team scaling to AWS needs to prevent simultaneous state corruption.
And the trap is assuming the storage service handles everything. S3 alone does not support state locking. You must pair it with DynamoDB.
Right. Now, HashiCorp's own managed service, Terraform Cloud, handles both storage and locking natively behind the scenes. But if you are configuring a custom remote backend in AWS, S3 is for storage, DynamoDB is for locking.
And the exam will offer multiple choice options like S3 with versioning enabled to throw you off, right?
Yeah, and versioning is great for backups, but it does not prevent the race condition.
Yeah.
Only DynamoDB provides the lock.
Okay, so we have our blueprint in the steel vault, and we have the bouncer managing the line. Everything feels very secure, but that sense of security brings us to a rather uncomfortable truth about what is actually written on that blueprint.
Yeah, the contents of the state file represent arguably the most critical security vulnerability in the entire Terraform ecosystem.
Wait, really? The most critical?
Yes, because any data that passes through your Terraform code database passwords, API tokens, TLS private keys, master user credentials.
Wait, are you saying those end up stored in Plain text?
Yes, completely plain text inside that tfstate JSON file.
Okay, wait, here's where it gets really interesting. In today's zero-trust security climate, where we use tools like HashiCorp Vault or AWS Secrets Manager specifically to keep credentials encrypted, Terraform just leaves our most critical database passwords in plain text inside this JSON file. Why isn't HashiCorp automatically encrypting those specific lines?
It seems crazy, but it comes back to the core mechanism of how Terraform detects drift and calculates dependencies.
Okay, how so?
Well, a one-way hash works perfectly for logging into a website, right? Because the server only needs to verify if the hash of your typed password matches the hash in its database.
Right.
But Terraform needs to actively compare the desired state in your code with the actual state of the infrastructure. If it hashed a database password in the state file, it couldn't easily retrieve the original value to pass it to a dependent resource.
Oh, like an application server that needs that exact password injected into its environment variables during provisioning.
Exactly. If the password is scrambled in memory, Terraform can't hand it over to the next resource that legitimately needs it. It has to be able to read its own memory clearly.
Okay, I see. But that functional requirement of plaintext memory turns the state file into a treasure map for hackers.
It absolutely does, which is why the security model shifts entirely to perimeter defense. You don't try to encrypt the individual lines inside the JSON file.
You encrypt the entire file at rest.
Yes, and you heavily restrict who can even knock on the door of the vault.
So imagine a company undergoing a strict security audit. The security team runs a pipeline scan and flags that several high-level database passwords are being exposed. They trace it back to the infrastructure as code deployment. The security team wants to know where Terraform might be leaking them and what they should do.
Well, they need to look directly at the remote backend configuration. The immediate remediation is locking down the IAM permissions on the S3 bucket.
Right, so you implement a policy ensuring that only the automated pipeline role, and maybe a break glass administrator role, has read and write access to that bucket.
Exactly. Developers should not have direct access to read the state file.
And then you turn on server-side encryption for the S3 bucket itself, ideally using a custom KMS key. So the vault itself scrambles the paper while it is sitting on the shelf.
And the IAM policy ensures the bouncer turns away anyone who doesn't have absolute clearance. Securing the perimeter is the only valid solution here.
Which really highlights why local state is so dangerous from a security perspective, too. A plain text file sitting on a developer's laptop is a massive compliance violation.
It's a huge red flag.
Okay, so given that this file is a highly sensitive, fragile JSON document that dictates the reality of your cloud, how are engineers actually supposed to fix things when the code and the state inevitably get out of sync?
Right, because they...
Yeah. If I rename a database in my Terraform code because of a naming convention update, but I absolutely do not want Terraform to destroy the actual production database and build a new empty one, we need a way to intervene.
And that intervention is what the industry refers to as state surgery.
State surgery. I love that term.
Yeah, and surgery requires precision instruments. HashiCorp provides a specific suite of CLI commands under the Terraform state umbrella designed strictly for this purpose.
Okay, let's break down the essential commands you must memorize for the exam. Let's look at the observational tools first, like Terraform state list and Terraform state show.
So, list provides a high-level inventory. It simply prints out the address of every single resource currently tracked in the state file.
It's like the table of contents.
And if you need the granular details of one specific item from that list, its exact tags, its deployed IP address, or yes, its plain text password, you use Terraform state show followed by the specific resource address.
But those are non-destructive, right? They just read the memory.
Exactly.
The heavy hitters, the actual scalpels for the surgery, are Terraform state MV and Terraform state MApp. Let's go back to my naming convention issue. I changed the name of a critical server in my code from web server 1 to front-end app.
Okay.
If I just run a normal apply, Terraform looks at its memory, doesn't see front-end app, and assumes it needs to build it. Worse, it sees web server 1 in its memory, doesn't see it in the code anymore, and assumes it needs to destroy it.
Which causes a catastrophic outage.
Yeah.
And this is the exact use case for Terraform state MV. The MV command stands for move.
So it moves or renames resources in the state without destroying the actual cloud infrastructure.
Yes. You are essentially telling the state file, the physical resource you currently track under the address web server 1 should now be tracked under the address front-end app.
You are just updating the address book.
Exactly. Next time Terraform runs, it sees front-end app in the code, matches it to the new address in the state file, and says, Everything matches, no infrastructure changes required.
That is incredibly useful. Now, the ROM command remove is equally critical, but it serves a different purpose. It tells Terraform to entirely forget a resource, right?
Yeah, it deletes the record from the state file, but it leaves the actual resource running in the cloud.
I have seen this tested heavily on the exam. A common scenario is an engineer needing to hand over a massive database to a specialized, separate database management team.
Right, the DBA team.
Yeah, and the DBA team doesn't use Terraform. They use their own manual tools. So the engineer needs to delete the database from their Terraform code repository to clean things up.
But if the engineer just deletes the code block and types apply, Terraform will execute a destroy command against the production database.
Which would be a resume-generating event.
Oh, a very bad day. To perform a safe handoff, the engineer first runs Terraform state arm, targeting that specific database address.
So that severs the link between the blueprint and the house. Terraform suffers localized amnesia.
Beautifully put. Once the resource is removed from state, the engineer can safely delete the code. The next time Terraform runs, it won't see the code, and it won't see the memory of the database.
It just ignores the database entirely, leaving it safely running for the DBA team to take over.
Exactly. And the final command you need to know is Terraform state pull, which is pretty straightforward.
It just downloads the remote state file, right?
Yeah, it downloads a raw copy from S3 to your local machine, usually so you can pipe it into a tool like JKey to parse the JSON for auditing purposes.
But having the pull command kind of brings up a dangerous temptation.
Oh, it really does.
If the state is literally just a text file sitting on my computer or an S3, why can't I just open it in Notepad, fix a quick typo in a resource name, hit save, and push it back? Why go through all these complex CLI commands?
Because of the complex dependency graph we discussed earlier, the JSON structure is not just a flat list of text. It contains intricate, nested pointers indicating which resource relies on which other resource.
So it's woven together.
Yes. If you open that file manually and delete a block, you might leave behind a dangling reference. Furthermore, Terraform relies heavily on Go's internal JSON package to parse this file.
And parsers are picky.
Very. If you leave a single trailing comma, which is so easy to do when manually editing JSON or mess up a bracket indentation, the parser will fail completely.
And then the memory is irreparably corrupted, not by a race condition this time, but by a manual syntax error.
Precisely. The Terraform state CLI commands are the only safe way to operate because they automatically recalculate those dependencies, format the JSON perfectly, and ensure the structural integrity of the file remains flawless. Manual editing is universally considered an anti-pattern.
Okay, so that really covers the landscape.
Yeah.
For everyone preparing for the exam, understanding these mechanisms is the difference between guessing and knowing. So let's summarize the absolute essentials. State is the ultimate source of truth. It is the memory that bridges your code to reality. It must be protected from team collisions using tools like DynamoDB to lock it.
Because S3 alone is not enough.
Right. And it holds our deepest secrets in plain text, so we have to use perimeter defense. And finally, we must only ever perform surgery on it using the official CLI commands, no notepad allowed.
Respecting the integrity of the state file is basically the foundation of mastering infrastructure as code. Terraform relies on you to protect its memory so it can accurately manage your reality.
But, protecting that memory reveals one final, really fascinating puzzle for you to think about. We've spent all this time talking about how Terraform state is the definitive memory of your infrastructure.
Right.
But what happens if a rogue developer goes directly into the AWS console and manually changes a server size, completely bypassing Terraform?
Ah, configuration drift.
Exactly. Suddenly, Terraform's perfect memory no longer matches reality. The blueprint says one thing, but the living room says another. How does Terraform handle that rift between its truth and the real world?
Understanding exactly how Terraform detects that rift and the mechanics of how it forces reality back into alignment with its memory, well, that is the next crucial layer of the puzzle to explore on your own.
It is indeed. Thank you for joining us on this deep dive into Terraform state. Keep learning, keep questioning how the mechanics actually work under the hood, and we will catch you next time.